Hello friends, I am Professor Nisar Ahmed Khan from Department of Economics, Aligarh Muslim University. Today I will talk about best linear unbiased estimators. What do you mean by best linear unbiased estimators? And these best linear unbiased estimators gives us best estimates and unbiased estimates. Now this best linear unbiased estimator property, in short, it is known as BLUE, B for best, L for linear, and U for unbiased, and E for estimators. So, there is we have already in my last lecture, I have talked about the population regression function and sample regression function. Now, this population regression function that we have, it is the value of U that we have here, the disturbance term, and the values of independent variable. Regarding them, we have certain assumptions. And if those assumptions are satisfied, then our estimators, the least square estimator that we introduced earlier in my earlier lecture, that least square estimator will be unbiased as well as best one. So, what are these assumptions? The first assumption is that this random term, U is a random variable. That is the assumption that we have already mentioned that U is a random variable. A random variable is a variable which takes its values by chance. So, in a case of random variable, the values are given, and along with the values, the probability of these values are also given. Now, the mean of this random variable is 0. That is, the expected value of this random variable is 0, because since it is a random variable, sometime it will take the positive values, sometime you take negative values, and if you find out the mean value, that is expected value of ui, then it will be 0. Then this variance is constant, that is, in the variability in U is constant. It is not going to vary from period to period. Throughout it is constant, because if it is not constant, then there will be problem in making forecasting and prediction. Then two values of U, namely ui and uj, are independent, that is, they are not correlated at all. That is, there is no correlation between the two, and if there is a correlation, then you will face the problem of autocorrelation, where a variable is going to be related with its own values. That is, the value of U in one period is related with the value of U in another period. Then ui is completely independent from the independent variable. That is, here we have x as independent variable. Now, x has given it is a given set of values, it is not a random variable, whereas u is a random variable. So, these two should be unrelated, there should be no relation between the two. And then this x, the independent variable, it is a set of fixed values, and only then it will remain independent if it independent variable, and if it is going to change, then it will no longer be an independent variable. So, by definition, you know that it should be a set of fixed values. Then these, if we have more than one independent variable, for example, we have x1 and x2, then it is also important that these two independent variables, that is x1 and x2, are not correlated. If there is a correlation between the two, and the correlation is a very strong one, then you will have a problem which is known as multicollinearity. Then the model is correctly specified. This is the assumption, that there is no specification error in the model, and that is variability in x values. That is not very important assumption, but the important thing is that x should be a set of fixed values. So, the classical this population regression function along with this assumption is known as classical linear regression model. We call this as classical linear regression model. Now, if all these assumptions are satisfied, by the model, then we will have our least square estimator will be unbiased and will also be best. So they have mentioned here BLUE stand for best linear unbiased estimator, and estimator is said to be BLUE if here there are three properties that it should have. The estimator will be called as BLUE provided it is linear and it is unbiased and it has minimum variance. These are the three properties it should have. So we have Gauss Markov theorem, about which we just told you that it mentioned the same thing, that as given the assumption of the classical linear regression model, if all the assumptions given above are correct, then the least square estimator will be having minimum variance in the class of linear unbiased estimator. That is what we call as Gauss Markov theorem. So the least square estimator that we obtained in my last lecture, we talked about least square estimator. So those least square estimators are best. That is, they have minimum variance but not best, in absolute term. They have minimum variance in the class of linear unbiased estimator. That is very, very important. That is not the case that least square estimator have least variance. They have least variance, but in the class of linear unbiased estimator compared to other estimators who are linear as well as unbiased. So comparison is made with these linear unbiased estimator and not with all the estimators. So now we will show you that how these least square estimators are best, and how can we show that they have minimum variance and they are unbiased and they are also linear. So let us start that. A proof for properties, the properties of this least square estimator. So we have, let us write first the population regression function y is equal to alpha plus beta x plus u. Now remember, here I am not writing yi, xi and ui, and I have told you that this is just to save time and make the things more complicated. So I am avoiding, but it does not mean that you should also write. You should write y, xi and ui as it. Though this is our population regression function, our population regression line. Then we have sample 1, that is y is equal to alpha hat plus beta hat x plus e. E is the sample residual and this is the population residual. You can call this is sample disturbance term, you can call it as population disturbance. So alpha hat and beta hat are the least square estimator. So what we will show that these estimators are linear, unbiased, and they have minimum variance in the class of linear unbiased estimator. So instead of showing for both alpha as well as beta, I'll show it only for beta. So we have told you that what is the value of beta hat in the earlier lecture. The beta hat is equal to summation small x small y divided by summation small x square. This is the beta hat, the least square estimator. Now this small y, I have told you that as far as x is concerned, it is x minus x bar, and as far as small y is concerned, it is y minus y bar. So these small x and small y are expressed in deviation form, whereas capital X and capital Y are expressed in actual, these are actual values, so that you should remember. So substituting the value of y here, small y, which is y minus y bar, if we substitute the value of y here, this y minus y bar, then what we will have here, let me write it directly, we will have summation small x y divided by summation small x square minus y bar summation small x divided by summation small x square. Now here we have y bar, which is constant. This is mean of y, and this summation small x means that is x minus x bar. We know sum of the deviation from mean. Since this is the mean, the deviation of x from mean, if you take the sum, it will always be 0. So summation small x is equal to 0. That is sum of the deviation from mean is 0. Not only this, the summation small y will also be 0. So using this property, we can write that beta hat will be equal to, this will be equal to summation small x capital Y divided by summation small x square. Now this we can write as summation W, we can write it as summation W and Y, where W is x divided by summation small x square. If W is denoted by small x divided by summation small x square, then beta hat can be written as summation Wy, that is this one. So beta hat is equal to summation Wy. Now substituting the value of y here, this value of y, that is alpha plus beta x plus u, substituting this value, what you will have substituting this value, we will have alpha summation W plus beta summation W x plus summation W u. This is what you will have. Now let us say that what is this summation W and summation Wxi. We told you that as far as W is concerned, it is x divided by summation small x square. So summation W will be equal to summation small x divided by summation small x square. We have already told you that summation small x is 0, so therefore this will become equal to 0. So summation W is 0. That property you should remember, that summation W is equal to 0. Now let's have Wxi. This is W is this one. So summation W x, summation Wx, that is this is capital X, this is not a small x. Summation Wx will be equal to summation small x, small x, it will be small x multiplied by capital X. So let me remove it, so that is, yes, it is summation small x multiplied by capital X divided by summation small x square. Now this capital X, if small x is equal to x minus x bar, so what will be x? Capital X will be small x plus x bar. So substituting this value of capital X here, we can write that summation Wx will be equal to, summation Wx will be equal to summation, substituting this value of x here, this value of x we will substitute, it will be summation small x square minus divided by summation small x square minus x bar summation small x divided by summation small x square. So we know that summation small x is 0, that we have told you. So this expression will become 0, and this divided by this is 1. So, summation W capital X is equal to 1. So, what we find that summation W is equal to 0, that is, let me write it here, summation W we find that it is equal to 0 and summation W X is equal to 1. So, using these two, that if summation W is 0, then if the summation W is 0, then this alpha summation W will become 0, and if summation Wx is equal to 1, this will be beta. So, we will have beta hat will be equal to beta plus summation Wu. So, if you take the expected value of beta hat, the expected value of beta hat will be beta, because expected value, this is the population parameter, its expected value will be same. So, plus summation W and expected value of U. Now, if you remember the first assumption of the classical linear regression model, or the second assumption, that expected value of U is 0 because U is a random variable, and if it is so, then expected value of beta hat is equal to beta, which means that this beta hat, that is this our estimator, least square estimator, it is an unbiased estimator. Now, you may say, what is this unbiased estimator? Unbiased estimator means that there is no systematic error. Now, error will be there, that if you have population estimate and if you have sample estimate, then there is likely to be difference between the population parameter and the sample estimate. The difference is inevitable. What we actually want, that this difference which we are calling as error, this error should not be systematic. If it is a systematic error, then that cannot be eliminated. Whereas, if this error is non-systematic, then if we conduct the experiment again and again, that takes sample again and again and find out the sample estimates and compare with the population parameter, then sometimes this error will be positive, sometimes this error will be negative. If we take the mean value of the error, then positive error will cancel the negative error, and we will have that expected value of our this estimator beta hat will be equal to beta, that is, mean value of the sample estimate will be same as the population parameter. So, provided the error is not a systematic one, the error is a random one. So, this expected value of beta hat is equal to beta. It means that the least square estimator will not give any systematic error, and consequently it is unbiased. So, this proves that least square estimator is unbiased. Now, as far as linearity is concerned, the least square estimator are linear by definition. If you look at the equation, then these least square estimators are linear by definition, no need to prove, and this least square estimator are also unbiased. Now, we have to show that least square estimators have minimum variance in the class of linear unbiased estimator. But before that, we have to find the variance of our least square estimator, that is beta hat. So, the variance of beta hat will be equal to expected value of beta hat minus beta square. This is the variance of beta hat, that expected value of, in the bracket, beta hat minus beta whole square. This is the variance of beta hat. This is the same formula of variance that you have studied in statistics. There is nothing special about. Now, as far as beta hat minus beta hat, we can obtain from here, beta hat minus beta will be summation Wu. So, we can write it as variance of beta hat will be equal to expected value and in the bracket we have summation W U whole square. Now, what is this summation WU? It is summation WI and where I start from 1 goes up to n. That we have told you in the beginning that I am not writing I, so that you can, that much adjustment you can make yourself. So, it means that this is like this. If you remove this, then this will be, it will be summation W square U square plus 2 summation I summation j, and there will be Wi, there will be Wj and Ui and Uj. So, we are forced to write I and j here because there was no other option. Sorry. Yes. So, these are two, Ui is one value, that is Ui and Uj, and Wi and Wj, this is Wj, let me remove this, this is Wj. So, this is the expected value of summation W square U square. I have no time to explain that, otherwise I would have explained this expression, how to obtain from this and this. That is, you know, you can yourself do this exercise. So, this is this. So, if we take the expected value inside, then this will be summation W square, and if we take the expected value of U square, expected value of U square, rather we can write in this way, there is no need of bracket, we can write simply expected value of U square plus this will be 2 summation I summation j Wi Wj and expected value of Ui Uj. Now, you may ask why I have not taken the expected value of W. If you look at W, W is small x divided by small summation small x square. So, W is composed of x, and x is a set of value, is a set of fixed values. So, if you take its expected value, you will get the same value, and that is why there is no point in taking the expected value of W here as well as W here. And we know, if you remember the assumption of the classical linear regression model, that the expected value of Ui and Uj is equal to 0, that is, two U's are unrelated, they are not related with each other. So, this will be 0, it means this entire expression will become 0. This will become 0, and consequently what we will have, and then expected value of U square is sigma square. So, we write it as sigma square summation W square. So, sigma square is the variance of U, which is constant. It is constant. That is the assumption, you know, of the classical linear regression model, that variance of U, that is disturbance term, is constant. So, this is sigma square is the variance of disturbance term U, and it is constant, multiplied by summation W square. So, what is summation W square? Now, let us find that. W is equal to small x divided by summation small x square. So, W square will be, that is summation W square, rather in one go we can take, it will be summation small, it will be summation small x square divided by summation small x square, this is raised to power 2. So, this will be equal to 1 upon summation small x square, that is summation W square, because this is 2, 1 will get cancelled. So, it will be 1 upon summation small x square. So based on that, we can write it as sigma square and 1 upon summation small x square. That is the variance of beta hat. We have to show that this variance of beta hat is minimum in the class of linear unbiased estimator. Now let's see how we are going to show that the least square estimator beta hat has minimum variance. What we will do, that we will take another estimator, and that estimator is also a linear unbiased estimator, and with that we will show that this estimator, this least square estimator has least variance. So let us move to another one, but this will bring back. Suppose we take this one, the beta hat. This is the estimator. We take here, we write in a different way. We write it as summation Cy, where C is a weight, and this weight has to be chosen in such a way so that the variance of beta hat is minimum in the class of linear unbiased estimator. So first of all, we have to show that this estimator beta hat is unbiased estimator, because we have to simply show that it has least variance. That is not enough. We have to compare the variance of least square estimator with the variance of other linear unbiased estimator. So first we have to show that this is an unbiased estimator. So what we do, that we substitute the value of y, that is here this value of y, alpha plus beta x plus u, this value of y we can substitute here, and if you do that, then this will be alpha summation c plus beta summation cx plus summation cu. Now, you cannot prove that beta hat is an unbiased estimator of beta unless we have two assumptions. The two assumptions are that summation c should be equal to 0 and summation cx is equal to 1. These are the two assumptions that must be satisfied. Only then we can show that here beta hat is an unbiased estimator of beta. Suppose these two assumptions are satisfied. If this is so, then beta hat will be equal to beta plus summation cu. So if we take the expected value of beta hat, then it will be equal to beta plus summation c, expected value of u, and expected value of u will be 0. So therefore expected value of beta hat will be equal to beta. Expected value of beta hat is equal to beta, that our estimator is unbiased. So this estimator is also unbiased, but under these two assumptions. Now let us find out the variance of beta hat here. The variance of beta hat here will be equal to the expected value of beta hat minus beta whole square. This is the variance of beta hat. So this will be equal to expected value of, now this beta hat minus beta is summation cu. So we will write here summation cu whole square. This we can write as we have done earlier, just now we did it. This we can write as expected value of summation c square u square plus 2 summation I summation j ci cj ui and uj, the bracket is closed. If we take the expected value here, then this will be summation c square and expected value of u square, plus 2 summation I summation j ci cj expected value of ui and uj. Expected value of ui and uj we have already told you will be equal to 0, and this expected value of u square will be sigma square. So what you will have is sigma square summation c square. This will be the variance of beta hat. We have to show that this variance of beta hat is minimum, and this minimization can take place only in case of c square, because as far as sigma square is concerned, sigma square is constant. No minimization or maximization is possible here, because this is the variance of u which is constant. So if it is constant, no question of minimum. So minimization of only summation c square, that we have to select that value of c, the weights have to be selected in such a way so that the variance of beta hat is minimum. But this is not, a type of free minimization. There are certain constraints, and the constraints are that summation c is equal to 0, summation cx is equal to 1. So this becomes a problem, that we have to minimize the variance of beta hat subject to these two constraints, that summation c is equal to 0 and summation cx is equal to 1. So this is a problem of constraint minimization. So you'll use the Lagrangian function, and you will write only this one. There is no point writing here, because this is not going to be changed. So we'll write here Lagrangian function, and this Lagrangian function will be summation c square minus 2 lambda, the first constraint, that is summation c. It is constraints are written in such ways that this is equal to 0. This has to be written. This will become summation cx minus 1 is equal to 0, minus mu, 2 mu. In the bracket we have summation c x minus 1. This is the Lagrangian function. This is phi, and we have to differentiate with respect to c, because we have to select the values of c, those values of c for which this variance of beta hat is minimum. So minimization of this with respect to summation, this with the constraint that summation c is equal to 0 and summation cx is equal to 1. So this is the Lagrangian function that we have written. Now we differentiate this phi with respect to c. When we will differentiate this phi with respect to c, we will have 2c minus 2 lambda minus 2 mu x, and for minimization the first order condition is that we should equate to 0. Then we will differentiate phi with respect to lambda. Lambda and mu are the Lagrangian multiplier. So with respect to lambda, and we will have here summation c as equal to 0. Now we will differentiate phi with respect to mu, and if we differentiate this with respect to mu, it will be summation cx minus 1 as equal to 0, which we can simplify as summation cx as equal to 1. That we can simplify. From here we can simplify, and summation cx is equal to 1. Now we take this one, 2c, 2 lambda minus 2 mu. So we can remove 2. You can divide this equation by 2. So what we will have here, that c minus lambda minus mu x, this is equal to 0. We have removed 2, we can divide it by 2. So, taking sum, suppose we take summation c minus n lambda, that is summing lambda n times, minus mu summation x, this is equal to 0. And we know summation c is equal to 0, so it can be written like this. Summation c is equal to this, taking this on this side, we will see that it will become n lambda plus mu summation x, and this is equal to 0. This is summation c is equal to 0, so the n lambda plus mu summation x is equal to 0. So, what will be lambda? Lambda will be that we have to take n on this side, it will be minus, I am writing it here, minus x bar. Because if you take n, if you take this on this side and divide it by n, then summation x divided by n will be x bar, so it will become minus mu x bar. This will be the value of lambda. This value of lambda we substitute here. Value of lambda we substitute here. If we substitute here, then this will become, this will become plus, because here it is minus and it is also minus, so it will become mu x bar minus mu x. This is equal to 0. So, we can write it, take the sum over all observations. So, this will be summation c plus or there is no need to take this so this one, this mu x, we can take this 2 on this side, it will be mu, and this will become x minus x bars. Yes. So, we have written these two have been taken on this side, this will become plus, this will become minus, same thing is written here. So, c will be equal to mu small x. This is, now let us see what will be summation cx. Summation cx, if we substitute the value of here, if c is equal to mu x, so then this will become mu summation small x multiplied by capital X. That here we are multiplying by x, here also multiplying by capital X and summing over all observation. So, summation cx will be mu multiplied by summation x multiplied by summation x. And this is equal to, cx is equal to 1, that we have already shown you that cx is equal to 1. So, mu summation small x multiplied by capital X is equal to 1, which means mu will be equal to 1 upon summation small x multiplied by capital X. Now, what is this small x? Small x, I have told you, small x is this x minus x bar. So, capital X will be equal to small x plus x bar. So, here substituting this the value of capital X, we can write it, it will be 1 upon summation small x, and then we substitute here small x plus x bar, because we substitute this value of capital X here and it is small x plus x bar. So, this will become equal to 1 upon summation small x square, this when you multiply this, and this will become plus x bar summation small x. And we know that summation small x is equal to 0, that we have already told you. So, this mu will become simply, this mu will be become equal to 1 upon summation small x square. Now, if we substitute this value of mu here, that is this value of mu is substituted here, then C will be equal to x divided by summation x square. So, the value of C which minimizes the variance of beta hat is this one, x divided by summation x square, and this is also the value of W that I have told you that W is equal to this, which is part of the least square estimator. It means that the value of C which minimizes the variance of beta hat is same as the value of W. Consequently, our least square estimator has minimum variance in the class of linear unbiased estimator, because this estimator that we have taken is also linear as well as unbiased estimator. It is linear by definition. Unbiasedness we have proved, and we found that the value of C which minimizes the variance of this beta hat is same as the value of W. Hence, beta hat has minimum variance. This proves that the least square estimator beta hat is best linear unbiased estimator. That's all. Thank you very much.